Hello, and welcome to Unit 1 of Operations Management Full Course, Introduction to Operations Management. Before we begin, we'd like to introduce the academic facilitator of this lecture. The learning materials used throughout this course have been developed by S.S. Christina, an award-winning entrepreneur, educator, innovator, and guest speaker with qualifications in information technology and business administration. Our goal is to provide high-quality, academically structured learning resources for university students and lifelong learners. Over the next series of lessons, we are going to build a solid, working foundation in what operations management is, how it works, and why it matters, not just in textbooks, but in real businesses every single day. To support your studies, we have compiled a complete learning package. You can find links to lecture notes, worked examples, practice questions, and more in the video description below. Before we dive into definitions, I want you to think about something simple. Think about the last time you ordered food online. In just a few minutes, a restaurant cooked your meal, a delivery partner picked it up, and it arrived at your door. That sequence, from raw ingredients to your doorstep, is operations management in action. Operations management is one seamless process, but it involves many moving parts. By coordinating every step, from sourcing to delivery, we create and deliver real value. Let's take a quick look at our learning objectives for this unit. These are the things you should be able to do confidently by the time we finish. In this unit, we will explore the production functions and the 6Ms model, define production management responsibilities, analyze automation, and learn how to calculate productivity. All right, let's start with the definition. Operations management is the management of an organization's productive resources, converting inputs into products and services. Every word matters here. Productive resources, these are the things you manage: people, machines, materials, money, methods. Converts inputs, there is a transformation process happening. Raw things go in, finished things come out. Products and services, notice it says both. Operations management applies to a car factory and to a hospital and to a bank. We'll look at this through three lenses: classical, behavioral, and modeling. Let me explain each one. The main idea of this concept is simple. Find the most efficient way to perform a task. Frederick Winslow Taylor, known as the father of scientific management, believed that every job has one best method. Instead of allowing each worker to perform a task differently, managers should carefully study the work, develop the best procedure, train employees to follow it, and continuously monitor performance. Let me explain this concept with a real-world example so we can get a better idea. Imagine a bottled water factory. Every bottle follows exactly the same process: washing, filling, sealing, labeling, quality inspection, and packaging. Every worker knows their specific task. Every machine has a schedule, and quality is checked regularly. If one machine begins producing fewer bottles than expected, managers investigate the problem immediately and correct it. Everything is standardized because the goal is maximum efficiency, minimum waste, and consistent quality. The second concept is behavioral management. Unlike classical management, this approach argues that people are not machines. During the famous Hawthorne studies, Elton Mayo discovered something surprising. Productivity increased not because the lighting or physical working conditions improved, but because employees felt that someone cared about them and valued their contribution. In other words, people perform better when they feel respected, involved, and motivated. Think about a hospital. Two hospitals may have the same equipment and technology, but one hospital has supportive managers, teamwork, open communication, and recognition for employees. Which hospital is likely to provide better patient care? Most people would choose the second one. This school reminds managers that motivation, leadership, communication, and teamwork directly influence organizational performance. The third concept is known as the modeling school. Here, managers rely on mathematics, statistics, and computer models to make better decisions. Rather than guessing, they analyze data and choose the best possible solution. The modeling school uses mathematics and systems thinking to support data-driven decisions. Whether it's linear programming or queuing theory, these models help optimize resources and reduce operational risk. Imagine an airline. Every day, the airline must decide how many aircraft to schedule, how many crew members are needed, which routes should operate, and how to minimize delays while keeping costs low. These decisions involve thousands of variables and cannot be made accurately by intuition alone. Instead, companies use mathematical optimization models and computer simulations. For complex systems like airline operations, mathematical modeling allows for real-time adjustments. By simulating thousands of variables, companies can optimize flight schedules and crew usage for maximum efficiency. In summary, modern operations management brings together these three schools of thought: the efficiency of classical management, the human focus of behavioral management, and the data-driven precision of modeling. These three schools are not competitors. They complement one another. A successful manufacturing company needs classical management to design efficient production processes. It needs behavioral management to motivate employees, build teamwork, and improve communication. And it needs modeling to analyze data, forecast demand, optimize production schedules, and reduce costs. Consider Toyota as an example. Toyota standardizes work processes to improve efficiency, invests heavily in employee involvement and continuous improvement through the Kaizen philosophy, and uses sophisticated mathematical models to manage inventory and production planning. By combining all three approaches, Toyota has become one of the world's most efficient automobile manufacturers. Modern operations managers rarely rely on just one school of thought. Instead, they combine efficiency, people management, and data-driven decision-making to achieve operational excellence. Let's define production as a system using the 6 M's: men, machines, materials, money, methods, and management. The 6 M's. Let me say them and explain each one quickly. Men, the human workforce, from floor workers to supervisors to managers. Human skill, experience, and motivation are inputs. Machines, all physical equipment, factory machinery, computers, vehicles, medical devices, whatever converts raw material into output. Materials, raw materials, components, parts, the physical stuff that goes into the product. Money, capital investment, working capital, cash flow. Without financial input, nothing else can happen. Methods, the procedures, techniques, and processes used to do the work, how the transformation happens. Management, the planning, organization, and control that keeps the whole system running. These inputs enter a transformation process to create goods or services. The output is either goods produced, tangible physical products, or services rendered, intangible outputs like healthcare, education, or financial advice. And notice the feedback loop, the arrow going back from output to input. This is crucial. A production system doesn't just flow forward. It monitors its output, measures quality, checks performance, and feeds that information back to adjust the inputs and process. This is what distinguishes a managed production system from a random one. Production is called a primary business function, alongside marketing and finance. Let me explain why that matters next. Let me put production in its proper place within the organization. Think of any company you know. There are 3 primary functions. Marketing figures out what customers want and creates demand. Finance provides the money to make it happen. Production actually makes it. Without production, marketing has nothing to sell, and finance has nothing to fund. Consider these facts. Production typically employs the largest number of people in a manufacturing organization. Production is responsible for the largest portion of a firm's assets: machinery, equipment, inventory. Production has a direct and measurable impact on the quality and cost of what the organization delivers. That's why the textbook calls production the heart of any organization. And just like the heart, it affects everything else. A weak production function means poor quality, high costs, missed delivery dates, and eventually unhappy customers and shrinking revenues. So when a CEO wants to improve competitiveness, the production function is almost always at the center of the solution. Now let's look at what production management actually does day to day. Planning comes first. Before any production can happen, someone has to decide what to produce, how much to produce, when to produce it, and what resources are needed. Planning encompasses product planning, what will we make, facility planning, where and with what, and conversion process design, exactly how will we transform inputs to outputs. Organizing is about structure. Once you have a plan, you need to build the organization that will execute it. Who does what? Who reports to whom? What tasks are grouped together? Organizing assigns authority and responsibility across the production system. Without clear organization, even perfect plans fail in execution. Controlling is where the rubber meets the road. Controlling means comparing actual performance against planned performance and taking corrective action when there's a gap. This requires good data, clear standards, and the authority to intervene. A simple example: a pharmaceutical factory plans to produce 10,000 tablets per hour. Organizing sets up the teams, equipment, and shift structure. Controlling monitors the production line every hour, and if output drops to 9,000, a controller identifies why and fixes it. That continuous cycle of plan, organize, control is the heartbeat of production management. The major objective of all this is to produce quality goods and services at the right price, at the right time. The modern production manager pursues optimal resource use, waste minimization, statistical quality control, and quantitative decision-making techniques. The scope of production management divides naturally into two broad categories: designing the system and then running it. Designing activities happen before production begins. You are engineering the production system itself. This includes tool design and technical drawings, the blueprints for every operation, equipment selection and installation, what machines, where, in what configuration, plant location, one of the most consequential and hard-to-reverse decisions in business. Getting location wrong costs a company for decades. Plant layout, how the factory floor is arranged, which directly affects efficiency and flow. Materials handling, how raw materials, components, and finished goods move through the facility. Control activities happen during and after production. They keep the running system on track. Production planning. This is day-to-day scheduling. What gets made this week, in what quantity, using which resources. It also means maintaining records of raw materials and finished inventory. Production control. This is real-time monitoring. The production manager tracks whether plans are being executed. If a machine breaks down, a supplier is late, or a worker is absent, control systems detect the problem and trigger corrective action. And within production control, there are three subsystems: inventory control, managing stock levels of materials, work in progress, and finished goods; work in progress control, tracking items on the production line; quality control, using statistical methods to ensure output meets specifications. Together, these designing and control activities define the full professional scope of the production manager's role. No production manager works in isolation. Let's look at the 5 key interfaces, how production management connects and must cooperate with other functions in the organization. First, marketing. Marketing is the intelligence function. It tells production what customers want, in what quantity, and by when. Strategic positioning and market segmentation decisions made by marketing directly determine production strategy. When production and marketing work well together, organizations achieve significantly higher effectiveness. Second, finance. Finance and production must collaborate on capital equipment decisions, cost control, and inventory management. Finance provides data on product and service costs that help evaluate operational performance. Production managers need working knowledge of budgeting, financial procedures, and investment evaluation. Third, design and R&D. Product life cycles are shrinking. Getting products to market faster requires tight integration between designers and production managers. Simultaneous engineering, where design and production planning happen in parallel, is increasingly standard practice. Process engineering directly determines how products can be made. Fourth, human resources. Production relies on people. HR handles recruitment, training, motivation, and increasingly flexible working arrangements. In services, customer-facing HR decisions directly determine customer perception. Fifth, information systems. ERP, enterprise resource planning. Systems integrate production with all other functions in real time. CIM, computer integrated manufacturing, brings IT into the factory floor itself. Knowledge management and e-commerce are reshaping how production processes are designed and executed. The key takeaway: production management measures the effectiveness of people, processes, and technology, and it must do this in constant dialogue with every other function. Automation. This is one of the most transformative forces in modern operations management, and it has been for over 70 years. The formal definition: the self-controlling operation of machinery that reduces or dispenses with human communication or control when used in normal conditions. Let me translate that. In normal operation, an automated system runs itself. It monitors its own performance, adjusts its own parameters, and maintains its own output, without a human having to intervene at every step. Did you know automation was first introduced in the late 1940s by the Ford Motor Company? Ford's automated engine plant in Cleveland, Ohio, used transfer machines that could move engine blocks automatically from one machining operation to the next without manual handling. This was revolutionary. Since then, automation has evolved to combine sophisticated physical devices with complex algorithms to improve operational efficiency globally. But today, automation is everywhere, not just in car factories. Think of ATMs, automated banking, airline check-in kiosks, automated customer service. Hospital robots? Hospital robots are specialized automated systems deployed to assist medical staff with repetitive logistical tasks, enhance precision in the operating room, and provide patient comfort. Amazon warehouses? Automated picking and packing. And now, AI-powered customer service chatbots, automated financial trading, self-driving delivery vehicles. Engineers design automation systems by combining physical devices, motors, sensors, actuators, with mathematical control algorithms and organizational workflows. The result can be extraordinarily complex. And as we will see in the next two slides, automation has both significant advantages and serious disadvantages. Understanding both sides is essential for any operations manager.
Automation has clear, compelling advantages. Let me walk through the key ones. 1. Replacing tedious tasks. If a task is highly repetitive, tightening the same bolt 500 times per shift, automation can do it faster, more accurately, and without fatigue. This frees the human worker for tasks that require judgment, creativity, or interpersonal skill. 2. Dangerous environments. This is a compelling case for automation. Would you want a human worker inside a nuclear reactor, or welding in an environment with toxic fumes, or working on an ocean floor? Robots can operate in conditions that would kill a human being. This application of automation has saved thousands of lives. 3. Superhuman capability. There are tasks that are physically impossible for humans. Handling components at temperatures of 1,000 degrees Celsius, or assembling microchips that are a few nanometers wide. Automation extends what humanity can manufacture. 4. Economy. At scale, automation dramatically reduces per unit cost. A robot arm may cost $100,000, but if it replaces 3 workers over 10 years, the economics can be compelling. But now the disadvantages, and these are real and serious. Technology limits. Despite rapid progress, there are tasks automation cannot yet do reliably. Anything requiring fine motor dexterity combined with judgment, like picking irregular-shaped fresh produce, is still largely manual. Unpredictable development costs. This is a critical business risk. Automating a production process can cost far more than estimated, sometimes making the entire investment economically unjustifiable only after the money has been spent. High initial investment. A fully automated automotive body shop costs hundreds of millions of dollars. That capital must be justified by future savings, which requires accurate demand forecasting. If demand drops, the fixed cost burden is brutal.
A key challenge in operations is distinguishing between goods and services. Understanding their differences in tangibility, inventory, and capacity requirements is essential for designing effective operations.
Tangibility. Goods are physical. You can see a car, touch a washing machine, count boxes on a shelf. You can inspect goods before the customer receives them. Services, a haircut, a medical consultation, a flight, are intangible. You can't inspect a service before it's delivered. The customer experiences it as it happens. Another important difference is how value is created. In manufacturing, value is created by physically transforming raw materials into finished products. For example, a furniture company converts wood into a table, adding value through processing and assembly. In services, value comes from the customer's experience, convenience, availability, or satisfaction. For example, when you visit a salon, the value is not a physical product, but the quality of the service and the overall customer experience. Process design is also very different. In manufacturing, production can usually take place without the customer being present. Factories are designed to maximize efficiency, speed, and consistency. In services, the customer is often part of the process. A hospital, restaurant, or bank must design its operations around customer interaction, waiting times, communication, and service quality.
Inventory. This is perhaps the most fundamental operational difference. You can make 10,000 cars and store them in a car park, selling them over months. You cannot make 10,000 medical consultations and store them. Services are consumed at the moment of production. This means capacity planning for services is fundamentally different and harder. Capacity. For goods, you design production capacity to match average demand and buffer with inventory. For services, a hospital emergency department, an airline check-in counter, you must design for peak demand. Because if demand surges and you have no spare capacity, customers can't wait. They go to a competitor. Quality. In manufacturing, you can achieve extraordinary precision through automation and process control. You can measure a component to fractions of a millimeter. Service quality is harder to define and harder to control because human performance varies and because customer perception of quality is subjective. Location. A car factory can be built wherever land, labor, and logistics are cheapest. A retail bank branch, a hospital, a restaurant must be located where the customers are. In simple terms, manufacturing focuses on efficient production, while services focus on efficient customer experiences. Today, the boundary between goods and services is blurring. Mercedes now offers remote software repair via internet. Xerox reframed itself as a document management company, not a photocopier seller. These hybrid models create fascinating and complex challenges for operations managers.
Productivity is a foundational concept in operations management. It defines the relationship between the output produced and the resources, or inputs, used in that process. Essentially, it measures how efficiently an organization creates value. Productivity. This single concept is central to competitive strategy, to national economic growth, and to the daily decisions of every production manager. Productivity equals output divided by input. That's the formula. But don't let its simplicity fool you. At the most basic level, if I use 100 units of input and produce 150 units of output, my productivity is 1.5. If my competitor uses the same 100 units of input but produces 200 units of output, their productivity is 2.0. They are more productive. And over time, that gap translates into lower costs, better prices, higher margins, or all three. At the national level, productivity determines the standard of living. Countries with high productivity generate more wealth per hour worked. This is why productivity growth is a key economic policy objective for governments worldwide. But productivity is not just an efficiency number. The concept has evolved. The textbook describes how green productivity, a program launched by the Asian Productivity Organization in 1994, extended the concept to include environmental protection and social well-being. You can't claim high productivity if you're generating it by polluting rivers or exploiting workers.
Operations managers typically utilize 3 types of productivity measurement: labor productivity, multiple factor productivity, and total factor productivity. Each provides a different analytical perspective on operational efficiency.
Labor productivity is the simplest. It measures how much output one unit of labor produces in a given time period. In India, coal mining productivity might be measured in tons per person per shift, OMS, or output per man shift. If one miner produces 2 tons of coal per day, OMS equals 2. But labor productivity has a serious flaw. If a company outsources half its workforce to external contractors and its own headcount drops, labor productivity appears to rise because the denominator drops while output stays the same. Nothing actually became more efficient. This is why single-factor measures can be very misleading. Multiple-factor productivity is more sophisticated. It combines labor, capital, materials, energy, and other inputs in the denominator. The formula is output divided by the sum of all input costs. This gives a much more realistic picture of overall operational efficiency. The challenge with multiple-factor productivity is that outputs are sometimes difficult to define. The textbook gives a great example: a fast food restaurant. Do you measure productivity by customers served per hour? Items sold? Different products have different values, so simple counting can distort the picture. Total factor productivity is the gold standard. It captures the year-by-year change in output considering all factors, not just the quantifiable ones, but also management quality, labor relations, worker attitudes, and even climate conditions. It's harder to calculate, but much more meaningful as a true indicator of economic efficiency. As an operations manager, you will use all 3, depending on context. For day-to-day operational decisions, labor productivity is quick and useful. For strategic investment decisions, total factor productivity gives you the full picture. Michael Porter's generic strategies are one of the most powerful and enduring frameworks in all of management. Every production strategy ultimately serves one of these 3 competitive positions. Number 1, cost leadership. The firm attempts to be the lowest cost producer in its industry. This does not mean the cheapest product, it means the lowest cost to produce. If you have the lowest cost structure, you can choose to sell at a low price, winning on volume, or sell at a market price, earning superior margins. Cost leadership requires relentless operational efficiency, scale, process innovation, and tight cost control throughout the supply chain. Number 2, differentiation. The firm identifies attributes that customers care about and excels at them in ways competitors cannot easily replicate. Premium materials, exceptional design, superior reliability, outstanding service. Xerox redefining itself as a document management company is a differentiation move. Apple's design-led products are a classic differentiation strategy. The production function must deliver consistent, superior quality, which often means higher costs, justified by higher prices. Finally, focus. Instead of targeting the whole market, the firm picks one narrow segment and serves it better than anyone else. A focus strategy can be cost-focused, the lowest cost provider in the niche, or differentiation-focused, the most premium option in the niche. Real-world examples illustrate these strategies clearly. 1. Cost leadership. Example, IKEA. Think about IKEA. IKEA designs furniture that customers assemble themselves. Flat pack packaging reduces transportation costs, warehouses are highly efficient, and products are standardized. Because IKEA keeps production and logistics costs low, it can offer affordable prices while remaining profitable. 2. Differentiation. Example, Apple. Apple rarely competes by offering the lowest price. Instead, customers pay more because of elegant design, seamless integration between devices, premium quality, and a strong brand image. Customers buy the experience, not just the product. 3. Focus strategy. Example, Rolex. Rolex does not try to sell watches to everyone. Instead, it focuses on the luxury watch market. Its customers value exclusivity, craftsmanship, and prestige rather than low prices. Enhancing productivity requires clear objectives. Knowing what productivity is and knowing how to improve it are two different things. Let's look at how operations managers actually drive productivity gains. We want efficiency, doing more with less. We want maximum output from given resources. We want economy, lower per unit costs. We want quality, because defects and rework are waste that kills productivity. We want to eliminate all forms of waste, anything that uses resources without adding value. And at a societal level, we want human satisfaction, employment, fair wages, better living standards. 3 powerful levers for improving productivity. Lever 1, technology, innovation, and automation. Technology determines the maximum physical output achievable from given inputs. Numerically controlled machine tools, robotics, CAD/CAM systems, AI-driven quality control, all can dramatically increase productivity. The key is that technology must be chosen economically. Switching costs are high. Once you build your process around a particular technology, changing it is expensive and disruptive. Lever 2, learning and experience. The experience curve, first observed in the aircraft industry, shows that as cumulative production volume doubles, per unit cost falls by a predictable percentage, typically 10 to 30%. Workers get better at what they do. They find faster methods, they reduce errors. This is a naturally occurring productivity gain, but it has to be managed, measured, and exploited deliberately. Lever 3, job design, work analysis, and motivation. Frederick Winslow Taylor's scientific management, analyzing every movement, every second of a worker's actions, was an early form of work analysis aimed at productivity improvement. The famous Hawthorne studies showed that motivation alone, just making workers feel observed and valued, increased productivity without any physical change. A motivated workforce is a productive workforce. This is one of the most cost-effective productivity improvements available to any manager. Now let's talk about one of the most interesting puzzles in economics, the productivity paradox. Nobel Prize-winning economist Robert Solow famously said, "We see computers everywhere except in the productivity statistics during this period." What does that mean? From the 1970s to the 1990s, organizations spent billions on computers and information technology. Logic said this should improve productivity dramatically, but the data showed almost no improvement in service sector productivity statistics during this period. The computers were everywhere, the productivity gains were nowhere to be found. Several explanations were proposed. Service sector productivity is hard to measure. How do you measure the productivity of a lawyer, a teacher, or a financial advisor? The metrics we use may simply fail to capture real value creation. Also, early computers were slow and required significant workarounds. The productivity gain was largely consumed by the learning curve and adjustment costs. But here's what's really interesting from an operations management perspective. Within the same industry, using the same technology, paying the same wages, some companies achieved dramatic productivity improvements, while others saw none. The difference was not the technology. The difference was whether the technology was used with intelligent focus, whether managers actually redesigned their processes around the technology's capabilities, rather than just automating existing inefficient processes. The lesson for your career: technology alone doesn't improve productivity. Thoughtful process redesign around technology does. And looking forward, the digitalization of the economy, smart devices, broadband, AI, should deliver productivity gains comparable to what mechanization delivered in the 20th century. The network effect, the more people use these technologies, the more valuable they become, will amplify these gains. The productivity paradox may eventually give way to a productivity boom. Now we move from theory to calculation. This section is important for your assessments. We will work through formulas and a complete numerical example. The fundamental formula: productivity equals output divided by input. That's it. But the way we express this formula varies depending on context. OMS, output per man shift, is used in manufacturing and mining. If a coal miner produces 2 tons of coal per day, their OMS is 2 tons per day. Simple, measurable, directly comparable between workers, shifts, or time periods. SMH over AMH, standard man-hours earned divided by actual man-hours worked, multiplied by 100 to express as a percentage. This is the most common formula used in factories with incentive schemes. Let me explain the terms. Standard man-hours earned. How many hours worth of work, at standard pace, did the actual output represent? If the standard time to produce 1 unit is 5 hours, and you produced 100 units, you earned 500 standard man-hours. Actual man-hours available. How many real working hours were available in the period? If 4 workers each work 25 days per month, 8 hours per day, that's 800 hours, minus any allowed delays. If productivity equals 83%, that means the workers produced 83 standard hours worth of output for every 100 actual hours available. The remaining 17% represents waste, time lost to delays, breakdowns, quality issues, or underperformance. And that 17%? That's our next concept, wastivity. Let me now walk you through the complete worked example. I'll do this slowly and clearly so you can follow every step. Wastivity. This is one of the most elegant and practically useful concepts in operations management. The formula? Wastivity equals 1 divided by productivity, or when expressed as a percentage, wastivity equals 100 minus productivity percentage. So if your productivity is 83.33%, your wastivity is 16.67%. That 16.67% represents resources that were consumed without generating any useful output. Let me be very concrete about what waste looks like in practice. Capital, money that could be doing something else, that is waste. Machines, waiting to be loaded. A CNC machine that costs $200,000 per year, sitting idle for 3 hours a shift because the operator is slow to load it, that idle time is pure waste. Jobs orders, waiting to be processed. Every hour a customer order sits in a queue represents service waste. Patients, waiting in a clinic. This is waste for the clinic. Idle consulting rooms, paid staff serving no patients. And it's also waste for the patient. Their time has value. And perhaps most important, defective production. When a product fails to meet specifications and must be scrapped or reworked, every resource that went into it, materials, labor, machine time, energy, is wasted. You've consumed inputs and got no usable output. Now, the resource refers to makes a striking claim. Reducing scrap by just 1% saves an organization more than a 10 to 15% increase in production and sales effort. Think about that. It's far easier and cheaper to stop wasting what you have than to work harder to produce more. This is why lean manufacturing, Six Sigma, and total quality management focus obsessively on waste elimination. Wastivity is the enemy. Zero wastivity, perfect productivity, is the ideal. Let's now work through the numerical example. Here we go, the worked example. Follow along carefully and make sure you understand each step. This is exam material. The problem: a manufacturing unit has a standard time of 5 hours per unit. In a particular month, 126 units are produced. The facility employs 4 workers. The working pattern is 25 days per month, 8 hours per day. Allowed delays total 44 man-hours. Find productivity and wastivity. Step 1. Calculate ESH, earned standard hours. ESH tells us how many hours worth of work at standard pace did our actual production represent. Standard time per unit equals 5 hours. Units produced equals 126. ESH equals 5 times 126 equals 630 hours. That is the value of what was produced, expressed in standard hours. Step 2. Calculate total available hours. Workers equals 4, working days equals 25, hours per day equals 8. Total equals 4 times 25 times 8 equals 800 hours. This is the gross available time. Step 3. Calculate AMH, actual man-hours available for production. From the 800 gross hours, we subtract allowed delays of 44 hours. AMH equals 800 minus 44 equals 756 hours. In Unit 2, we move to product and service design, where we learn how the decisions made before a single unit is produced determine the operational performance that follows. See you there.
To continue your learning journey, you can access additional course materials, practice with multiple choice questions, and explore revision resources. New content is added regularly to help you build strong foundations in operations management.